So, good afternoon. Welcome to our new astrophysical seminar. Our guest today is Oliver Müller from the University of Strasbourg, who will tell us about the use of dwarf galaxies as a test for standard cosmology. Concerning Oliver's CV, he got the master and the PhD from the University of Basel under the supervision of Bruno Bingeri. He was the last astronomy student ever in Basel, because after he graduated there was no more astronomy anymore, but he still got the Amberbach Prize for the best dissertation, which is one of the highest, prize you can get for your thesis at the university there. And now he's a postdoc at the Observatoire of Strasbourg in France, and his main collaborators, where you can see listed them here, say Rodrigo Ibata, Benoit Famey, and Pierre Landuc. So the stage is yours. You can speak 20-25 minutes, and then we have questions later. Please.
Perfect. It's great to finally speak about science again. And today I want to convey actually one key message. If by the end of the talk I have convinced you on this message, I'm actually quite happy. And my take-home message is dwarf galaxies are cool. These critters, these faint galaxies, dwarf galaxies, are the most abundant type of galaxies in the universe. They are also the most dark matter dominated galaxy in the universe, and because they are so faint, they only consist of a few stars. And they are red, and most of them are red and dead, so they are quite simple systems. And because they are red and dead, they are simple, and they are dark matter dominated. They are the perfect laboratory to study the effects of dark matter. So if we are interested in dark matter, then we should care about dwarf galaxies. Here I'm an observer, so I like to present observations. And here's, for example, a map of our local universe, so the so-called local volume. The local volume is a sphere of roughly 10 megaparsec around our point of view. And what you see here, I hope you can see my pointer. So this band, that's the Milky Way disk, so the zone of avoidance where we don't see anything. But the rest, the points, are galaxies. And you see that there's something odd on this this map. So normally I would now ask the audience what is wrong with it, but that's now difficult, so I just show it. The dwarf galaxies are missing. So if we ignore the dwarf galaxies, we don't get the full picture, especially the fine structure of the universe, of the structure of matter. So here I added the dwarf galaxies, and you can see that really some structures pop out. For example, I hope you see my pointer here in the middle. There's this band of galaxies. That's the so-called local sheet. Also, here is a zone to the left, is a zone where you don't see any galaxies at all. That's the local void. So really you have these different structures here, which are visible if you look into the dwarf distribution, and are not well visible if you just plot the giant galaxies. You can spot the local sheet, but it's much harder. So if we look into our standard cosmology, the lambda plus cold dark matter model, we feed the initial conditions from the universe into supercomputers and let it run for several billion years. We can create a map of how the universe should look like. So this is, for example, a map from the simulation, from the Millennium 2 simulation, and this is a dark matter only run. But I mean, dark matter is much more abundant than the baryon. So this is this approximation of how the universe looks like. So the densities are just the dark matter, so the dark matter distribution, the matter distribution in general. And what you see is that you see this filamentary structure. You see here, for example, these filaments, you see sheets, you see these clusters, and you also see these voids. So what we observe here in the local in our local neighborhood, we can reproduce in simulations. So there's an excellent agreement between observations and the large scale in our universe. However, if we look into the details, especially if we look into galaxies, groups of galaxies, dwarf galaxies, some tension starts to appear. Here I compile an incomplete list of some of the tensions which have been identified over the last few years. There's, for example, this cusp core problem where the shape of galaxy doesn't correspond to the predicted shapes of dark matter halos. There's the missing satellite problem where you have a mismatch of the simulated dark matter halos and the observed galaxies. There's the too big to fail problem, which in my opinion is just a flare of the missing satellite problem, which tells you that the brightest dwarf galaxies around giant galaxies, they somehow miss. So they should be visible because they are the brightest, but they are not apparent. So there is another interesting correlation also between the size of a bulge and the number of dwarf galaxies, which should not appear in the simulations, but we observe in the universe, in the real universe. But I'm going to talk about a particular problem, and this is the planes of satellite problem. So let's have a look into our own galaxy system, the local group, which consists of two giant galaxies. So on the right side, I show the Milky Way with its satellite, with its dwarf galaxy population. On the left side, Andromeda. And all this crosses here on the right and triangles, those are dwarf galaxies. And what you see is that the dwarf galaxies seem to be arranged in a planar structure. And this cannot really be explained by the zone of avoidance. So the Milky Way disk itself covering parts of the sky, which is indicated here. So these gray areas, we should be able to observe dwarf galaxies in all these wide regions. And what we see is that the dwarfs, they seem to be aligned in along this planar structure. A similar thing has been found for Andromeda, our neighboring galaxy. Here you see it to the left. And here only roughly half the satellites, so that half the dwarf galaxies reside in this plane. But what is indicated here with the colors is the motion. It seems that there is some kind of co-rotation. So on the one side, they are red-shifted, on the other side, they are blue-shifted. Seems like they are co-rotating around the Andromeda system. The same is found for the Milky Way. Especially in the Milky Way, you have proper motion measurement and line of sight velocities. So you really get the 3D information of the motion. And if we look into an edge-on view on this plane, like here, so we are now looking edge-on, and all these points are the dwarf galaxies, and here there are the vectors, so the motion. You see that several of them seem to be co-rotating around the Milky Way. One of them is not, one of them is like counter-rotating, and a few of them are also not taking part. But it seems that there's not only a planar structure, but it seems that the satellites themselves seem to orbit within this planar structure. And I like to see history, how with the evolution of data, how such things changed. And this is shown here on the left side. On the x-axis is the evolution in the years, and on the y-axis is the errors, the evolution of the error for these proper motion measurements. And what you see is that, with the advance of more and more data, the errors went down. So here, 20 years ago, we had mostly HST data, so Hubble Space Telescope data, and now, of course, we have Gaia 2, DR2 data, so the errors in the velocity measurement went down. On the right side, same thing, we have on the x-axis the year, and on the y-axis we have the deviation, so the standard deviation from the normals of these orbits. If we assume that there is like a perfect flat planar structure, and every object would perfectly co-orbit within this plane, the standard deviation would of course be 0 because all the normals would look into the exact same direction. But if you have some intrinsic scatter, some thickness, then of course the standard deviation will a little bit increase. If there is, let's say, a chaotic motion, there should be no correlation, so the standard deviation should be high. However, if there is some coherence, so if there is a coherent motion, then the standard deviation should get smaller. And what we see here is that with better and better data for taking 3 dwarfs, 4, 5, 6, 7 dwarfs, gets smaller and smaller over the years. So it's now at something like 20 degrees. So for 7 dwarfs, all the normals point within 20 degrees, which showed that with better data, the hypothesis that there is some correlation got better and better. But why do we actually care about that the dwarfs are in this planar structure and seem to co-rotate? I mean, the planets around the sun also do something very similar. So if we look again into the simulations and zoom into such vertices where like large galaxy groups or clusters reside, and compare what we predict and what we observe, then we find something strange. I mean, here would a Milky Way-like giant galaxy sit, and all these dots would be the dwarf galaxies. What you can see is, okay, there is some kind of flattening of the system, but it's not as flat as was observed. And also you don't see it here, but if you look into videos, the dwarf galaxies, so these subhalos, they should move quite chaotically. So we don't expect from simulations that there is some co-rotating motion within a plane. And of course, we can quantify this. This is, for example, done here. So on the x-axis, I show the thickness of the dwarf galaxy satellite system. And on the y-axis, I show this correlated motion. So how high is the correlation? How many are co-orbiting? The blue crosses are from analogs from Milky Way-like systems in the Millennium simulation, and red is just another simulation. It's the Elvis simulation. And the black dot is the observation of the Milky Way. We see that most of the analogs are thicker and most of the analogs are less coherent in their motion. So the Milky Way system is something like a 0.1 to 1% outlier. Only a few of the galaxies in the simulations behave as the Milky Way. Same thing can be done for Andromeda. And again, there you see that also the Andromeda is a 0.1 to 1% outlier. So in our local group, we have twice an outlier, and that's strange. So the question is the local group unique? Are we just this peculiar outlier, or are other galaxy groups in the nearby universe also show this behavior? And to test that, we need to actually follow 3 steps. We need to go out and find more dwarf galaxies around other galaxy groups. We need then, when we have identified them, we need to measure their distances to get the 3D distribution and measure their velocities. And if we have this information, we can compare this to cosmological simulations to see how well our standard model performs and if the local group is indeed an outlier or not. So we went to the next galaxy group. This is the so-called Centaurus A group. It's our closest neighbor in the southern hemisphere. It's at roughly 4 megaparsec, and it also consists of 2 giant galaxies. So we have Centaurus A down here, which is a huge elliptical galaxy. It's one of the largest galaxies in the nearby universe, and M83 up here. To search for dwarf galaxies, we have used the dark energy camera in Chile. It's the perfect instrument to study this because it has a huge field of view, and that's what is needed if you want to cover a large portion in the sky. So we search for dwarf galaxies in roughly 400 square degrees in the sky around this galaxy group. So that would be a talk on its own, how to find these dwarf galaxies. I just show here the results with red. So we have roughly doubled the number of known dwarf galaxies in this group. And while we were doing this survey, Brent Tully and collaborator proposed that around Centaurus A, shown here, the then known dwarf galaxies also reside in two planar structures. So I showed them here in red and in blue. So all these dots are dwarf galaxies, and there seemed to be an arrangement in this really two planar structures. And of course, we just had new dwarf galaxies, so we roughly doubled the number, and we started to get the distances so we could test if this really is the case. We did that with the Very Large Telescope, so an 8-meter class telescope. And to get the distances for these new dwarfs, we wanted to measure the tip of the red giant branch. So the tip of the red giant branch is a standard candle. You can measure the turn-off, so a red giant branch can only get as bright as its tip, because then afterwards the helium flash occurs, so it changes its position and its evolution. So we really know at what magnitude this occurs, and with that we can measure the distance. But for that we really need to get the red giant branches, meaning that we have to resolve these galaxies into their individual stars, and for that you need excellent seeing. We did it. Here is an example of two dwarf galaxies. On the left side, you see a discovery image with the dark energy camera. So you see here this faint blur, and also here this faint blur. So it's really hard to detect these dwarfs. And on the right side, you see the follow-up observations with the Very Large Telescope. And what you can spot is there are some more stars here. So much more stars than you see, for example, here. And these really belong to the galaxy. So if we plot a color magnitude diagram, this red giant branch appears. You see that here. And so the tip of the red giant branch, so the cutoff to the brightest red giants, give you then the distance. So we got it for more dwarfs. Some of them were really beautifully resolved into their red giant branch stars, some were not. If you see, for example, in the middle on the top, that this looks dwarfish, but it's probably a background dwarf galaxy. Or what I also find really interesting is the one in the right upper corner here. This galaxy was treated as a dwarf galaxy candidate for over 20 years. So here is the discovery image of this thing, and here are our follow-up images. And what you clearly see now is that, oops, that's actually a spiral galaxy. So you see here this spiral arm here or here. And now that you know that it's there, you can actually imagine that you see this also on the right, on the left side, right here and here. But sometimes you need follow-up imaging to get to the bottom of what an object actually is. So here again is a map of the dwarf galaxies as presented before. So you see there's two planar structures. One is here and the other one is here. And you see this gap in between those two. So we now got new data. Another group around Denia Zanojevic also got some more data. And the question is then, how does the satellite distribution look like if you add more data to it? It looks like that. So in red and yellow are the new data points. And yeah, they follow roughly the two planes of satellites. But also it starts to it starts to emerge that this gap between them starts to fill up. So what we can say is that indeed there is some flattening. I mean, you see that there's some, it's more elongated than it's wide. So there seems to be some flattening, some plane, or however you want to call it, some pancake. But is it two planes or is it only one extended structure? That's difficult to tell and at the debate at the moment. However, what is really important is that we see this flattened structure edge on. And if we imagine that there is like around the Milky Way or Andromeda, there is something like a co-rotating structure, and the structure is seen at edge on.
20 minutes.
Okay, yeah. If this structure is seen edge on, you would expect that on one side, when the satellites are moving towards you, they will be blue shifted, and on the other side, where they would move away from you, they are red shifted. So if you have a co-rotating plane of satellite there, blue and red shifted on opposing sides. So we went to the literature, and actually we found that for 13 of the satellites, 16 had velocity measurements, and out of these 16, 14 follow this motion as just described, that on one side they are blue shifted, on the other side they are red shifted. So this is a good indication that again, at the next galaxy group we observe, we find again this co-rotating plane of satellite. Of course, we can quantify now this again and compare it to cosmological simulations, here this time with Illustris, and we see the same thing emerge. So here's the thickness of the system, and here the motion. This all the crosses are the analogs in the simulations, and here this is the observation. So the green point is the observation, and we see again we are at this 1% outlier. And I want to make here the point that we call it the plane of satellite problem, but the flatness is not necessarily the problem. I mean, 14.5% are even thinner in the simulations than what we observe. It's the motion. We see that we don't expect to find co-rotation. And if we, of course, take these two things together, flattening and the motion, then we get this really low probability. So, of course, because there were more satellites there which didn't have any velocities, we also tried to get the velocities, again with the Very Large Telescope, this time with MUSE. And MUSE is excellent because it's a spectrograph which fills the dwarf galaxy fills up the full field of view. Because they are so faint, these dwarf galaxies, it's really hard to observe them just with a slit. So you need something like an IFU to get the spectrum. So we got spectra for 11 more dwarf galaxies. We got absorption lines, and with that, the velocities. So we could add 11 more dwarf galaxies into this to test this co-rotation, and this is what we get now. So here we have a position velocity diagram. So on the x-axis the position, on the y-axis the velocity, and again the triangles were the old data points, the 16 old data points. The squares are the new data points, and you see that most of them are following again this co-rotation. If there would be random motion, you would expect all the satellites be distributed in all 4 quadrants. If it's a rotation, only in 2 opposing quadrants. However, what is strange here is that not all of them following it. And if you just ask about the chance of finding this, just as a chance occurrence, 14 out of 16 or 21 out of 27, that's exactly the same chance. So the significance didn't increase, it did not decrease, it stayed the same, which I find is a little bit strange if you add more data for supporting or disputing a hypothesis and you get the same significance. I don't know at the moment what this is telling us. But I want to conclude here that, okay, the local group seems not unique in this respect. We go out, we observe the first galaxy group, and we find a similar problem. There have been 3 ideas on how these things have formed, but they are all compiled in this review recently written by Marcel Pawlowski. So if you are interested in that, then please have a look or ask me in the question and answer, because I prepared some of these explanations, but I just want to highlight one, which is specifically tailored to our local environment. And as I showed you before, we are sitting at this edge of this local void. Up here, we also have the Virgo cluster. And it looks like the planes of satellites are somehow arranged with our local sheet. So here we have the 3 normals. So like the direction E1 is the direction towards this local void. And it seems that the normals of these planes, at least for Centaurus and Andromeda, they are pointing towards the local void. So they are aligned with this local sheet. The Milky Way is not, and some other planes are also not really aligned. But this could tell us that perhaps this is a local effect. However, that would explain the planarity, but not necessarily the motion. I don't know how in this scenario motion is that the satellites will start to co-orbit around galaxies. So to conclude, I'm an observer, and as a proper observer, I say we need more data. And what I mean with that, we are still at a small number statistics. We have now observed 3 systems, and we cannot have a paradigm shift on 3 data. So we should observe now 10th of or hundreds of such galaxy groups and really test how well does Lambda CDM perform. Are all outliers? If we observe 100 galaxy groups and 100 of them are outliers, then there's something strange with our cosmological model. But if we are indeed just observing now the outliers by chance, then yeah, we don't need to change. So we need now really more data to get to the ground of that. And here are my conclusions. So thank you very much.
Okay, thanks, Oliver. Excellent talk. Are there questions for Oliver? Or I can, meanwhile, I have a couple at least. Yeah. So one concerns simulation. One of the last possible explanations we are proposing is the exceptionality, in a sense, of our local environment. Yes. So if I understand correctly, the comparison you have done, or I mean, it was in the other paper, was referring to the Illustris simulation. But
yes.
Okay, but there are also simulations that attempted, and there is a group in Potsdam, another group, trying to resimulate exactly the local universe. There is this clues, collaboration.
Yes, yeah.
Exactly. So if you use instead a cosmological setup which is tailored to reproduce the local environment, do you end up having the same problem or not? Is there an answer ready to be?
Okay, the thing is, Noam Liebeskind, who is the PI on this project, I talked with him, and I think they have results, but they could not yet share it. So I think they are very close in publication, and they will shed new lights.
Okay. So it's a pending issue. Okay.
Yes, but it would be really interesting because they really try to get the Virgo cluster right, the local group right, all this positioning they get right. So it would be really interesting to see if they get this out of it.
I know. Okay. And then coming to more or less one of your conclusion, more observation. So, given the present state of affairs, do you think it would be more important to have like deeper observations of nearby systems to be sure of the local dynamics, etc., or increasing the statistics, like producing a complete statistic in some sense, telling you, okay, given 10 groups of galaxies, I would expect to see this planarity effect in blah % of them. Okay, I understand both will be best, but at the moment, what would be the
I think actually the second option, so that you get 100 of satellite systems, because that would, let's say, here also with CERN, we have this special point of observation because it's very close. So we preferentially find planar structures where if we spot at this co-rotation. I mean, if it's a flat, if it's a face-on system, we don't see it. We don't see a rotation. So it would be easier if we just have a statistical sample with different orientations and everything. And we don't need 20 or more satellites. Let's say if we have 7 satellites, we can then test it, but around 100 groups. We can populate exactly this plot I show here and see if it is, again, if it is following the distribution from the simulation or if it's somehow otherwise distributed. I think that's the better way to go. Also, uncertainties. We'll get, let's say, the true 3D position within a group gets worse and worse the farther you go away.
Okay, but so far, even with, say, 7 members, the uncertainties on distance are not large enough to I mean, you can still be sure of all planarity effects, even with given the existing uncertainties on distance, say.
That's a little bit of a problem if you go farther away than CERN, then the uncertainties will become larger than the plane itself. So then you really cannot go for 3D, but only for 2D. And let's say if you see a plane edge on, that would just be the on-sky distribution of satellites, and that's like astrometry precise. So I would rather go for that, and let's say every galaxy group would host such a thing. Then just by chance, most of them we would not see because of their orientation. So with that, we could start, if we get a large number, we can also estimate, let's say, the frequency and how much do we miss by their orientation and stuff like that.
Okay, I see. Okay, thanks. Other questions for Oliver? Anybody from anywhere? Cosmologies, simulators, people doing dynamics.
Observations.
Observations, of course. Okay, if nobody's jumping in it, I think we can conclude. We're a bit longer than usually. Okay, thanks again. Let me stop the recording. So thanks for contributing.